Okay, so in this video, I'm going to explain to you guys reversible reactions and irreversible reactions. So we'll first have a look at reversible reactions. Reversible reactions are those reactions in which the reactants convert into products and the products then break down back into the reactants. Okay, so it's a really simple concept, and we'll take the example of Haber's process to understand it more better. So we've got, So we've got nitrogen plus hydrogen to give out 2NH3, which is ammonia. Okay, now nitrogen combined with hydrogen to form ammonia. Now, if you notice that in this reaction we used a different symbol that I don't think you guys would know if this concept's new to you. So basically, in what reversible reactions, the reactants combine to form the product, and the product can break down into the reactants. So in this case, nitrogen and hydrogen would combine together to form ammonia, and ammonia can break down back into nitrogen and hydrogen. Okay, so we'll have a look at the reaction symbol. So this was the symbol, right? And if you look at the symbol, it has two arrows, one going on in the forward direction and one going in the backward direction. So the forward direction means that, this means that these reactions have two reactions going on, in which one is forward reaction and the other is backward reaction. So forward reaction is basically in which reactants form products, and in the backward reaction, products break down into the reactants. Okay. And if you want a real life example of reversible reactions, we've got water. Okay. So if you freeze water, you get ice, and if you leave the ice outside at room temperature, it would melt back into water, right? So that's a reversible reaction. So we've got water. If you freeze water, you're going to get ice, and then ice can it can go back to its original form if you leave it at normal room temperature. Okay, so this is a real life example. Now let's go to irreversible reactions, and in irreversible reactions, the opposite happens, meaning that the products can't convert back into the reactants, they can't break down. So you've got reactants combining together to form the products, but the products can't break down into the reactants. Okay, and if you want an example of irreversible reactions, we've got magnesium oxide. So magnesium, it burns in oxygen. Magnesium burns in oxygen to form magnesium oxide. Okay, now in this reaction, first of all, we know it's irreversible by the symbol that's used, which is a single arrow, meaning that this reaction only goes in the forward direction and it can't go in the backward direction, meaning the product can't go back into its original form, it can't break down into the reactants. Okay, so this means that this reaction is irreversible magnesium oxide. Once magnesium oxide is formed, you can't get magnesium out of it, you can't get oxygen out of it. It's a irreversible reaction. Okay, and if you want a real life example of irreversible reactions, we've got cake. Okay, so you have all the dry ingredients, and when you combine them, so like you've got egg, you've got water, you've got flour, you've got, I don't know what else, you've got honey. When you combine those dry ingredients, you get a cake. Okay, but those dry ingredients, now once you get a cake, you can't get those dry ingredients out of it again, so that indicates it's a irreversible reaction. So dry ingredients, cake, and it can't convert back into its dry ingredients. Okay, and now we will do open system and closed system, since it's related to reversible reactions and irreversible reactions. So we have two systems going on, two containers. Okay, these look like containers, and one container is closed. Okay, so the black one, the one I'm coloring right now, is a closed container, and the purple one is an open container. So let's say there is two reactions. One reaction is going on in which basically A gas reacts with B gas to form C gas. Now this reaction is going on in this container, and it's going on in this container. Now what's the difference between an open system and closed system? So basically in an open system, it is going to interact with the other gases that are in the surrounding area. So the gases in the air, like oxygen, nitrogen, carbon dioxide. Okay, we've got pollutants. So these are natural gases that are in the air, and what's going to happen is, since the container is opened, it's an open system, those outside gases are going to interact with the reaction going inside, and they're going to interact with the reactants, and they are going to affect the product. Okay, whereas in a closed system, they don't have any interaction with the outside environment. So this is just a reaction with those reactants. There is no other gas interacting with them. Okay, and you're gonna notice that there's gonna be a difference in the products. Okay, so in the closed system there's gonna be a different product, and in the open system there's gonna be a different product. Okay, and there might be a difference in temperature as well, because according to the thermodynamics principle, temperature flows from a place of high temperature to a place of cold temperature. So for example, the outside environment, it has high temperature, and the inside environment of the container it's a cool place. It has low temperature. Heat is gonna flow in, so it can go in and it can affect the reaction's product. Okay, so this is the difference between an open system and closed system. In an open system, there is no interaction. There is an interaction of the reaction going on in an open system with the interaction of the outside environment, and in a closed system there isn't any type of interaction.